Hello, this is the 20th video on my multivariable calculus course. In this video, we're going to talk about triple integrals. Suppose the mass density of the solid E at point xyz is f of xyz, then the triple integral of f of xyz dz over E evaluates the total mass of this solid, and then we want to find out how to evaluate this triple integral. Let R be the projection of E onto the xy plane, and suppose E lies between two graphs of z equals g of xy and z equals h of xy, then the triple integral is the integral from bottom, which is g, to top, which is h, and then integral over the projection. So let me illustrate that in this diagram. So I have a solid E that is bounded below by some surface g of xy, z equals g of xy, above by some other surface, let's say z equals h of xy, and then we've got the projection onto the xy plane is some other region, and I call the projection onto the xy plane perhaps region R. So this is the projection onto the xy plane. How do we evaluate this triple integral? What we do is we go from bottom to top. So that gives us the limits of z. So z is from g of xy to h of xy. We integrate with respect to z, and then we integrate over the bottom, over the projection onto the xy plane. Now, if the region R is a horizontally simple region, then we use coordinate system, the Cartesian coordinate system. If it is vertically simple region, then we also use Cartesian coordinate system. And if it is a polar region, we use polar coordinates. And as we discussed, the triple integral over E of f of xyz dv evaluates the total mass. Because if this is density, when you multiply density by volume and then you take the total, that gives you the total mass. We will do some examples on this one, but before that, let's make a remark on this one. When the density is 1, then density is 1, so that means mass over volume is 1. What does that mean? It means mass is equal to the volume, which means the triple integral is not only the mass, but it is also the volume. So in order to find the volume of a solid, we just do the triple integral of 1 over that solid. So let's do some examples on this one. So here is the first example. Let E be the solid bounded by the planes x equals 2, x equals 5, y equals 0, y equals 3, z equals 0, and z equals 1. The very first thing you want to do is always to draw the diagram. So we need to draw two things. First, the solid, which we will draw. Next, the projection onto the xy plane. So x between 2 and 5. So we have this. I'm going to draw this, but I might have to erase whatever is not needed. Then y is between 0 and 3. So we have 0 here, we have 3 here. So y is between 0 and 3. So I don't really need this portion. I only need the portion from 0 to 3. So this is really all I need. And then z is between 0 and 1. So this is what I need on the z axis. So let's erase what is not really needed. So I'm going to turn that into a dashed line to make clear what the solid is. So this is our solid. So it's a rectangular prism. Now, this is the first thing we need to draw. We also need to draw the projection of this onto the xy plane. So let's see. What is the top of this solid? Well, the top of this solid is z equals 1. And what is the bottom of this solid? The bottom of solid is z equals 0. So this is the bottom, which is also the projection onto the xy plane. So this is our region R. So I always draw one diagram for the solid and one for the projection onto the xy plane. So let's draw that as well. So x is between 2 and 5. So this is 2, this is 5, and y is between 0 and 3. So this is the projection onto the xy plane. Now we will set up the triple integral and we will evaluate that. So triple integral over e of xy dv is what they're asking us to evaluate. So what we're going to do is we're going to do the double integral over the projection, and then we'll have to find the limits of z. So limits of z are bottom to top. So what is bottom? It's 0. What is top? It is 1. So it's integral from 0 to 1. Now we will have to decide what to do with this double integral. Well, is this region R horizontally simple or vertically simple? In fact, in this case, it is both. So we could use this region as a vertically simple or horizontally simple and put the limits of integration. I'm looking at this region as a vertically simple region, so I know the limits would be dy and dx. First, I would have to do dy, and then I would have to do dx. So this would be integral from 0 to 1, xy dz, and then dy dx. So what are the limits of y? We'll have to look at the bottom of R and the top of R. Bottom of R is 0, top of R is 3. Then the smallest value of x is 2, and the largest value of x is 5. So we will take this triple integral, turn it into a double integral, and then we use what we have learned about double integrals. So let's evaluate this integral. So it says integral from 2 to 5, integral from 0 to 3. This is dz, so we'll have to do xyz from z equals 0 to z equals 1 dy dx. This is going to be integral from 2 to 5, integral from 0 to 3. And then we'll have to plug in the values. When we plug in value of 1, we get xy. Then we will have to integrate that. We will get integral from 2 to 5. Integral of xy is xy squared over 2. And then we'll have to plug in values. Because I have two different variables, x and y, I will indicate which variable I'm substituting. So this would be integral from 2 to 5. I'm substituting 3 for y, so that would be 9x over 2. And for y equals 0, I will get 0. And then we're going to integrate this one, so this would be 9x squared over 4 from x equals 2 to x equals 5. Plug in the value, we get 9 times 5 squared over 2 minus 9 times 2 squared over 4. And this would be our answer. And of course, we can simplify this. So what does this answer mean? It means if you place an object on this rectangular cube and the density at every point is xy, if the mass density is xy, then the total mass is exactly the quantity that we found down here. So let's look at a few more examples. So I have the next example is evaluate the volume of the solid that lies above the above the plane z equals -2, below the surface z equals 1 minus x squared, in front of the plane x equals 0, to the right of the plane y equals 0, and behind the plane x plus y equals 1. Okay, so the very first thing we want to do is to draw a diagram for the surface, for the solid. And the next thing we're going to do is to draw the projection onto the xy plane. So this is the x-axis, this is the y-axis, this is the z-axis. Okay, so the first thing is above the plane z equals -2. So z equals -2 is down here. So -2 is down here, and it's above this plane. I will use dashed lines, but we'll complete the diagram after we draw all these different surfaces that they gave us. Below the surface, z equals 1 minus x squared. So what is z equals 1 minus x squared? It is a sheet. On the xz plane, it is a parabola. So the vertex is 1, comma 0. And it is this. And we're going to have to move this one. Of course, there's also a portion at the back. We're going to have to move the same thing along the y-axis in both directions. So some of what I'm drawing is not really necessary. We'll erase what is not necessary. And then the next part is in front of the x equals 0. So in front of what x equals 0 means I don't need the portion that is behind the yz plane. X equals 0 is the yz plane. To the right of the plane, y equals 0. So that means I don't need the portion that y is negative. So I don't need the portion to the left of the xz plane. And then finally, we have the portion that is behind this plane. Okay, so I'm going to draw the plane x plus y equals 1. This point is 1 because the parabola is 1 minus x squared, z equals 1 minus x squared, and that is equal to 0 when x equals 1 and negative 1, but we don't really care about the portion that is behind the yz plane. So the intercepts are 1 on both axes. So we have this plane, and then we have to basically take this line and move it in the z direction. So we will get this solid. So if we look at this, this is the solid that we're going to get. If we move this up, this is the solid that we're going to get. I'm going to erase the portions that aren't really necessary. So this is not necessary. I don't need this part. I don't really need this part, but I do need the top portion. So you have something like this, and there's a crease right here. So we'll have to identify the bottom and the top and the projection onto the xy plane. Okay, so what is the bottom and what is the top? So the bottom of this solid is the plane z equals -2. So that's the bottom. What is the top of this solid? Well, the top is z equals 1 minus x squared. So if I mark it here, this is the top of the solid. So this is the top. And what is the bottom? It is right here. So these are the two things we need to understand. And the third thing is the projection onto the xy plane. So this is what I call E. So the whole thing is E. And then we need to look at the projection onto the xy plane. Well, what is the projection onto the xy plane? It is the bottom triangle. So it is this one. And the intercepts are 1. So this is our region R. So now we are trying to find the triple integral of 1 dv. Why are we evaluating the triple integral of 1? Because the question is asking us to find the volume. So what is the volume? The volume is always triple integral of 1. So I'm going to first write that down here. So volume of E is equal to the triple integral of 1. Next, we're going to plug in the limits of integration, and then we will integrate. So the integrand is just 1. We look at this solid. Does it have a top? Yes. Does it have a bottom? Yes. Does the projection onto the xy plane, is the projection onto the xy plane a region that is horizontally simple, vertically simple, or a polar region? The answer is again yes. So this region is in fact a vertically simple region. The top of the region is 1 minus x, y equals 1 minus x, and the bottom is y equals 0. So because of that, we can switch to Cartesian and evaluate the integral. So the limits of z are going to be the bottom, which is -2, the top, which is 1 minus x squared, and then we look at the region R and we set up the limits of integration. Since this region is horizontally simple and vertically simple, we can do dy dx or dx dy. Limits of y are bottom to top. Bottom is 0. Top is 1 minus x. Limits of x are 0 to 1. Left to right. And now the rest is just evaluation of the integral. So 0 to 1, 0 to 1 minus x, and then we'll have to integrate with respect to z. So that's just going to be z evaluated from z equals -2 to z equals 1 minus x squared dy dx. Integral from 0 to 1, integral from 0 to 1 minus x. Then we'll have to plug in the values 1 minus x squared and then minus 2. So 1 minus x squared plus 2 dy dx. Next, we'll have to integrate that with respect to y. We get integral from 0 to 1. What is the integral of this with respect to y? Well, that's 3. So integral of that would be 3y minus x squared y, and we'll have to plug in y equals 0 to y equals 1 minus x, and then after that we'll have to integrate with respect to x. So plug in 1 minus x, we get 3 minus 3x. Plug in 1 minus x, we get x squared times 1 minus x, which is negative x squared, and then plus x cubed. Plug in 0, we get 0. So this is going to be equal to integral from 0 to 1. Well, let's just integrate this now. Integrate in respect to x, we get 3x minus 3x squared over 2 minus x cubed over 3 plus x to the fourth over 4, which is going to give us, this is from 0 to 1. If we plug in 1, we get 3 minus 3 halves minus a third plus 1 fourth. So this is our answer. And of course, this can be simplified. Let's move on to one more example. Consider the solid E below the paraboloid z equals 1 minus x squared minus y squared and above the plane z equals negative 3. Evaluate the triple integral of x plus 1 over E. So the first thing, as usual, is to draw the solid, draw the projection onto the xy plane, and go from there. Decide what coordinate system to use and go from there. Okay, so it's z equals 1 minus x squared minus y squared. So this is the surface. And they also said z equals negative 3. So I'll have to come all the way down to negative 3. So what is the intersection of these two? Well, the first one is a paraboloid. The second one is a plane. So the intersection is a circle. So the intersection of these two will be a circle. So something like this is what we're going to end up getting. So this is our solid E. Okay, what we're trying to do is trying to evaluate this triple integral. So again, we need two things. We need the graph of the surface and the solid, and we also need the projection onto the xy plane. So what is the projection onto the xy plane? Well, we'll have to look at the widest part of the solid. Well, the widest part is in fact the bottom. So this is the projection onto the xy plane, which I usually denote that by r. So what we're going to do is we're going to look at this r and decide what coordinate system to use. So if we look at r, we get a region that is not quite Cartesian. So it's best to use polar coordinates for this one. So we will do that. We have triple integral over E of x plus 1 dE. As we discussed, this would be double integral over R and then integral x plus 1 dz and then dA. So for that, we need to figure out what's the top and what's the bottom of this solid. So the top is the paraboloid, which is 1 minus x squared minus y squared. So top is z equals that. What is the bottom? The bottom is z equals negative 3. So the bottom is negative 3. The top is 1 minus x squared minus y squared. Now, because this is a polar region, it is best to switch to polar. So we can write this down as integral. So the radius here is 3 because it was, or no, actually we have to find out what the radius is. So we have 1 minus x squared minus y squared, that's the paraboloid, equals negative 3. So we get x squared plus y squared equals 4. So the radius is in fact 2. So now that we know the radius, we can write it down in polar coordinates. So this would be integral. We'll have to change everything to polar. So that's negative 3, 1 minus r squared. X is r cosine theta plus 1 dz. And since we are switching to polar, dA would be r dr d theta, which we have discussed before. Now, what are the limits of r from 0 to 2? We saw that the radius of that circle was 2. And then from 0 to 2 pi, because it's a full circle, we have points in all different quadrants. So this is the integral from 0 to 2 pi. We'll have to integrate with respect to z first. So integral from 0 to 2. Well, integral with respect to z would be r cosine of theta plus 1 times z. And then we'll have to plug in z equals -3 to z equals 1 minus r squared r dr d theta. So notice that r and theta are constant when you're integrating with respect to z. So what we can do is we can plug in the values. So 0 to 2 pi, 0 to 2. When we plug in 1 minus r squared and -3, we get 1 minus r squared plus 3, and then r dr d theta. How do we integrate this one? Well, this is a polynomial, so we'll have to expand and then integrate. So this would be integral from 0 to 2 pi, integral from 0 to 2. If we multiply this, so we can write this down as 4 minus r squared. If we multiply this, we get 4r cosine theta plus 4 if we multiply by 4. But there's also an r in front, so we get r squared and then r here, minus r cubed, which is going to be r to the 4th cosine of theta, and then minus r squared times r, which is r cubed, and then dr d theta. So what we did was we multiplied the inside out, and then we will integrate, because then it became a polynomial which we can easily integrate. Okay, let's go ahead and integrate this one. So this is integral from 0 to 2 pi. Integral with respect to r of 4r squared is going to be 4r cubed over 3 cosine of theta plus 2r squared, so 4r becomes 2r squared, minus r to the 5th over 5 cosine of theta minus r to the 4th over 4. And this is r equals 0 to r equals 2. And then finally we'll have to integrate with respect to theta. So we can plug in the values. We get 0 to 2 pi. When we plug in 2 here, we get 4 times 8. That's 32 over 3 cosine of theta plus 8 minus 32 over 5 cosine of theta minus 4 d theta. Once we integrate, some of these terms are going to in fact disappear. Integral of cosine is sine plus 8 theta minus 32 over 5 sine theta minus 4 theta. And this is theta equals 0 to theta equals 2 pi. Well, sine of 2 pi and sine of 0 are the same. In fact, both of them are 0, so we can ignore those. When we plug in theta equals 2 pi, we get here, we can combine these two. So these two become 4 theta. So 4 theta, and then when we plug in 2 pi, we get 8 pi. And when we plug in 0, everything else is going to be 0. Sine of 2 pi and sine of 0 are also 0. So this would be our final answer. So this is the triple integral that they asked us to evaluate. So what did we learn in this video? We learned that the triple integral evaluates the total mass as long as the integrand is the density function. Triple integral of 1 evaluates the volume, and in order to evaluate triple integrals, what we have to do is draw the solid E and draw its projection onto the xy plane. You change dv into dz dx dy or dz dy dx depending on whether your r is horizontally simple or vertically simple. Then you change the limit of z from bottom to top of your solid E. And notice that this could be a function of x and y. Then you look at your r, and then you find the limits of x and y using your region R. So that part is exactly what you do when you are doing a double integral in Cartesian coordinates. And if your R is a polar region, then you'll have to use polar coordinates. I will see you in the next video.